Okay, good morning or good afternoon or good day. In this video, we're going to be doing a little bit of review on what we've talked about with the electric potential energy and voltage for point charges, as well as the electric potential goodness gracious, the equipotential lines, and then working through some solutions to the problems that you had to work on for this week. All right, so first of all, while we didn't talk about this directly this week, I'd like to remind us of the relationship in general between the electric potential energy and the voltage. So specifically that the electric potential energy is equal to the charge times the voltage, right? So I've got some charge that's creating this voltage, and then if I put another charge in that voltage, it has an electric potential energy, which we can find using this equation. I can also look at this relationship and say that the change in the electric potential energy is that charge times the change in the voltage. So that's looking at two different points. What's the change in voltage between those 2 points? If I move a charge between those 2 points, what's the change to the electric potential energy between those 2 points? Now, specifically this week, we're looking at the equations to find the electric potential energy and voltage for point charges. So we wrote these down. And we're seeing a similar form to Coulomb's law, right? So the difference with the electric potential energy is that we've got an r in the denominator, not an r squared anymore. And we're also not taking the magnitude of the charges. The electric potential energy can be positive or negative. For the voltage, we're not squaring the Q in the numerator anymore, so it's just the single Q. That's our source charge. So sometimes we've been putting the subscript of Q1 to let us know that Q1 is the source charge, where Q2 is the charge that's in that field. So that both of these would be the charges Q2 that are experiencing that voltage. And then we've got the single r in the denominator, where in each of these cases, r is the distance either between the two charges, Q1 and Q2, or the distance from Q1 to whatever point that we're looking at. And again, with the voltage, we're not taking the absolute value of that charge, so it can be positive or negative. And then last, we were talking about equipotential lines, right? These lines that we're noting where the potential, the voltage, is equal. And we said that for charges, single point charges, to get a line that describes where the voltage is constant, we have to hold R constant. And if I hold R constant, I'm going to end up with something that is a circle. And so I'm going to have a series of circles that are slowly getting farther and farther apart, marking out these equipotentials. And these changes happen at a particular rate. So if, for example, this is 500 volts, right, maybe this next one is 400 volts, and the one after that would be 300, and so on and so forth. So they're usually changing at some sort of fixed rate. Okay, so with this little bit of review underneath our belts, let's start looking at some problems. All right, so first I've got a proton that starts from rest, 2 centimeters from a 3 nanocoulomb point charge. So I've got a little diagram drawn here with my big positive 3 nanocoulomb charge and then my small proton, and the distance r initial of 2 centimeters apart. And then I'm looking for the initial electric potential energy of the proton. All right, so the first thing I'm looking for is the initial electric potential energy. All right, I've got my knowns listed, so I did put down the thing that we know, but we aren't explicitly given, that the charge of the proton is a positive 1.6 times 10 to the minus 19, and then I also noted the mass of the proton, the 1.67 times 10 to the negative 27th, in addition to defining the other variables that are showing up in my diagram. So I've got 2 point charges, and I'm trying to find the electric potential energy, so I'm going to use that equation that we just finished writing down. So I'm going to take the 2 charges that I've been given, I'm going to multiply them multiply one another by that constant k, 8.99 times 10 to the ninth, and then divide it by that initial distance between those two charges. And if I plug this into a calculator, I will get an answer of 2.2 times 10 to the negative 16th joules, right? Joules being the unit for energy. All right, and then part B, I'm being asked to find the final speed of the proton. So we're talking about, right, letting the proton go. So saying that's free to move. It's going to start speeding up from the force from that other positive charge, right, moving away. But there's this point where I've essentially used up all of the electric potential energy that I started with. And after that point, the proton, right, is just going to continue moving in the same direction at a constant speed. All right, and so I'm starting with electric potential energy, and I'm transforming that into kinetic energy. All right, so this is a problem where I'm using the conservation of energy. So I can start with my equation that the initial total energy has to be equal to the final total energy. And in the initial state, since it's at rest, the only form of energy that I've got is the electric potential energy. And in the final state, since we're specifically given that the electric potential energy is 0, we're saying, okay, it's just got energy from the fact that it's moving, and so that's equal to the kinetic energy. So the electric potential energy initially we've got from before, so I'll just leave that variable as it is. But for the final kinetic energy, this is going to be equal to 1/2 times the mass of the proton times the final speed squared, right? Where the thing that I'm looking for is this final speed, and everything else in this equation I've got defined. All right, and so then I just have to solve. And I've got a final equation. Now remember, because we're treating the electric potential energy initially as an intermediate in part B, we need to include all those significant figures, so I might plug in a number that's more like the 2.1576 times 10 to the minus 16th joules, right, which was my answer before I rounded for the 2 sig figs that we have in this problem. Right, and when I do that, I should get a final speed of 508,326 meters per second, or again, in that 2 sig figs, 5.1 times 10 to the 5th meters per second. Okay. Looking at problem 2, we're using the diagram to answer the following questions. What is the electric potential of points A, B, and C? So in my diagram, I've got points A, B, and C. Those are on 2 different equipotential lines, and I've got that 2 nanocoulomb charge in the center. And so I just want to know the electric potential, or the voltage, or the potential, right, at those points. Then I'm going to be looking for the electric potential energy of an electron at these points. And then finally looking for the potential differences between points A and B and points B and C. All right, so let's start with part A. I'm looking for the electric potential, or the voltage, at A, B, and C. All right, so again, this is a point charge situation, so I can use the equation that we wrote down for the voltage of a point charge. All right, and if I'm looking at the voltage at point A, then I'm using that 1 centimeter distance, or what I've noted as R sub I, or the inner circle, so the inner radius. And I can calculate a value for that. In this case, I'm going to get a value for the voltage of 1,798 volts, or in the 2 sig figs that I've got for this problem, that'll be 1,800 volts. Now, one of the things that I can be noting is that points A and B are on the same equipotential line, so what I know right away without having to calculate it is that the voltage at B will also be in 1,800 volts. And then last, we can find this for point C, where the only thing that's going to be changing is what's in my denominator. So I've still got the KQ in the numerator, I've got the same source charge, but now we're just a little bit farther away, and so I've got to use that outer radius for that outer circle. The other thing that we can say before we do any calculations is that since we're farther away from our point charge or source charge, we should expect that the voltage is going to decrease, and that's exactly what we see, right, and get a value of 899 volts, or again in 2 sig figs, 9.0 times 10 to the 2 volts. Okay, for part B, I'm looking for the electric potential energy if I were to put an electron at each of these points. Right, so the electric potential energy at A, B, and C. And to calculate this, I am going to need to have the charge of an electron. So I'm going to put this down as Q2, which is the negative of that fundamental charge, or negative 1.6 times 10 to the minus 19 coulombs. All right, for part B, there's two ways that I can do this. The most straightforward way that I can do this is using that very first equation that we wrote down. So the electric potential energy is equal to the charge that's in that field, not the one that's creating it, times the voltage. And so what we're doing is we're saying, okay, if I just take the charge of that electron and multiply it by the voltage that I've found at each of these points, I'll find the electric potential energy at each of these points. And so if I do that, all right, again, because I'm using the same charge in each of these locations, because it's a electron that's at all of these points, since the voltages at A and B were the same, then the electric potential energy at A and B will be the same, so negative 2.9 times 10 to the negative 16th. And then for C, just taking the charge of the proton and multiplying it by the voltage at C. Remember that when we're calculating these second numbers, the voltages at A, B, and C are now intermediates, and so we need to use all the significant figures. So I'm not using 1800 volts to calculate the second part, I'm using the 1798, and same thing for the voltage at C. All right, and then last, I'm looking for the potential differences between the points A and B, and then points B and C. All right, and I'm reading these values as a charge, or moving from point A to point B, and then from point B to point C. So that's giving us a sense of what my final and what my initial are going to be. Now for the first one though, looking at the change in voltage between A and B, well, A and B are both on the same equipotential line, which by definition means that they are at the same potential. So if I'm looking for the change in the voltage between points A and B, we can say right off the bat that that has to be 0, right? Or I can do the calculation, right, which is going to be the voltage at B minus the voltage at A, final minus initial. And so I'm going to do the 1800 minus 1800, which is going to give me 0. All right, for the change in voltage at point B to point C, I'm going to take the voltage at C minus the voltage at B, right, final minus initial, and I should get an answer of negative 899 volts, or again in 2 sig figs, a negative 9.0 times 10 to the 2 volts for that difference. Okay, and then last, we're looking at the superposition, where we're saying to find the voltage from a bunch of different point charges, I just have to add them up. So we're looking for the potential at point A from the charges at points B, C, and D, moving counterclockwise around that rectangle, and then the potential energy of a proton at that point A. All right, so for A, I want to know what the potential at A is. Again, this is the same as electric potential or voltage, so what's the voltage at point A? And to do that, I'm just going to add up all of the individual voltages. All right, so I can say that the voltage at A is going to be equal to the voltage from the charge at B plus the voltage from the charge at C plus the voltage at the charge from the charge at D. All right, and then the denominators, I've got R, B, C, and D, so just how far is point B from point A, or C or D, so on. All right, so for point B, I'm looking at my diagram, it is the 4 centimeters from point A, so I can write this down in my list of knowns, right, that RB is the 4 centimeters, or 0.04 meters. For C, this is a little bit tricky because we're looking at the hypotenuse, but it's not too bad, all right, because RC is just going to be, using the Pythagorean theorem, the square root of the 2 centimeters on the top squared and the 4 centimeters on the side squared to give me a value. And then last, my distance for point D to point A is going to be that 2 centimeters, or 0.02 meters. All right, and so with all of these, I can plug in my values, and I should get a final answer for the voltage at A of 3,133.98 volts, or to two significant figures, 3,100 volts. All right, and then for the potential energy of a proton at A, again, I can do this 2 different ways. I could find the electric potential energy of adding them together from the charges at B, C, and D to get my final answer, or I can use what I've already found in part A. So I'm going to show you the second way because this is a lot simpler, right? And that is that the electric potential at the electric potential energy at A is equal to the charge that's at A. So that's going to be the charge of a proton. And I'm going to multiply that by the voltage that I just finished calculating at the point A. And so writing this another way, I'm going to do that positive fundamental charge, 1.6 times 10 to the minus 19 coulombs, times what I calculated in the last part, again including all of those significant figures, and I'll get my final answer for the energy, the electric potential energy at A, and that will be a value of 5.0 times 10 to the minus 16 joules. All right, I'm just going to remind everybody one last time that all of these units should be in base SI units, so all of these charges should be converted into coulombs. So this nano here, right, nano means 10 to the negative 9. Right, and I need to do that conversion to get the correct answer on all of these problems. Right, so all of these charges need to be in coulombs, all the distances need to be in meters. Right, all the charges need to be in coulombs, all the distances need to be in meters, and I suppose in this case the mass needs to be in kilograms in order to get the correct answer. All right, so that's it for this video. Check back here soon for a discussion on the electric field and potential in parallel plate capacitors.